Welcome to your favourite podcast.
Hello and welcome back to the Copper Connection podcast, where we unpack the science and engineering that keeps buildings alive and running. As always, I'm your host Chris Bailey, and today we are diving deep into the principles of mechanical science. The forces, the motions, the mechanisms that underpin so much of building service engineering, or BSE. From the precise movements of lifts and the powerful pushes of pumps to the careful design of ductwork and the structural integrity of supports. Every BSE engineer leans on these fundamental principles. Understanding them isn't just academic, it's crucial for designing systems that are safe, efficient and reliable. So, without further ado, let's get into this week's episode. First of all, we're starting off with energy. Energy is the lifeblood of our built environment. It is what allows us to heat our spaces, power our equipment, and light our rooms. In scientific terms, energy is defined as the capacity to do work. It's the fundamental currency of all physical processes. A core principle is the law of conservation of energy. Energy cannot be created or destroyed, only converted from one form to another. This means when you see electrical power of the fan, that the electrical energy isn't lost, it's converted into kinetic energy, the movement of air, and some heat due to the friction. The standard unit for energy is the joule, which you'll see in so many different calculations. We typically categorize energy into two main forms: kinetic energy and potential energy. So, kinetic energy is the energy of an object proposes due to its motion. Think of water rushing through a pipe, the blades of a fan spinning to move air, or the rotation component within a pump. The faster an object moves and the more mass it has, the greater its kinetic energy. Then we have potential energy. It's stored energy that depends on an object's position or state. A large water tank positioned high on a building's roof stores significant gravitational potential energy, which can be converted into kinetic energy to drive water flow through the building's plumbing systems by gravity alone. Similarly, a compressed spring in a valve stores elastic potential energy. So transducers are fascinating devices that perform these energy conversions. A photovoltaic panel, for instance, acts as a transducer by converting radiant energy from sunlight directly into electrical energy. An electrical motor converts electrical energy into mechanical kinetic energy to drive a pump or a fan. Even a simple light bulb is a transducer, converting electrical energy into light and heat. Now let's take a look at force. A force is fundamentally a push or pull that can change an object's state of motion or cause it to deform. While there are four fundamental forces in nature: gravity, electromagnetism, and the strong/weak nuclear forces in building services engineering, we primarily deal with gravity and electromagnetic forces, especially in electrical systems. The forces act as structures and systems in a building include gravity, pulling downwards. This is the constant and affects everything. Self-weight, the inherent weight of building components themselves, like a heavy boiler, a long run of steel ductwork, or a large air handling unit. Imposed loads, these are external forces applied to a structure, such as a heavy plant machinery placed on a rooftop, or the weight of snow on a roof. And then we have live loads. These are variable or transparent forces like the movement of people in a lobby lift, the dynamic pressure changes from water hammering pipes, or the wind loading on a building's fascia. The standard international units or SI units of force is a Newton. 1 Newton is defined as the amount of force required to accelerate a 1 kilogram mass at a rate of 1 meter per second squared. Crucially, a force always has both magnitude, how strong it is, and direction, the way it is applied. For a structural system to be stable and static, all forces acting upon it must be in equilibrium, meaning the perfect balance, and they balance each other out. If an imbalance occurs, structural elements will settle, deflect, or even fail, leading to aesthetics damage or worse, structural compromise. You might not see the force itself, but you will certainly see its effects. Now let's take a look at Newton's second law. Sir Isaac Newton's second law of motion provides a fundamental relationship between force, mass, and acceleration. He defined a force as anything that causes an object to accelerate. This relationship is expressed by the famous equation F equals ma. F is the resultant force, measured in newtons. M is the mass of an object, measured in kilograms. And A is the acceleration of the object, measured in meters per second squared. This equation tells us two key things. Firstly, the acceleration of an object is directly proportional to the resultant force applied to it. More force means more acceleration. Number two, the acceleration of an object is inversely proportional to its mass. A heavy object will accelerate less for the same amount of force. So now let's consider an example. If a large truck weighs 38,000 kilograms and needs to accelerate at 0.3 meters per second, the force required would be 38 kilograms times 0.3 meters per second, which equal 11,400 newtons. Now, would a small car need more or less force to achieve the same acceleration? Well, it would be significantly less because it's a much smaller mass. In building services engineering, Newton's second law is widely applied for stationary objects like buildings. The acceleration is zero, which means the sum of all forces acting upon it must also be zero for it to remain in equilibrium. Engineers use this principle to calculate the forces acting on the joints in the framework of the buildings, bridges, and even the stresses on pipe supports or the mounting points for heavy plant. When designing dynamic systems like lifts, pumps, or extraction fans, engineers use force equals mass times acceleration to determine the necessary motor power to move the specific mass. So the lift car, water, or air at desired accelerations. Now that moves us nicely into work and power. Understanding working power is crucial for sizing equipment and evaluating its system's performance in BSE. Work is done when force causes a displacement or movement. It's expressed as work done equals force times distance. Work done is measured in joules, force is measured in newtons, and distance moved is measured in meters. 1 joule of work is done when a force of 1 newton causes a movement of 1 meter. This means work can be also expressed in newtons meters. So, looking at an example, if a lift needs to move a person weighing 650 newtons up 50 meters to the top floor of a building, the work done is 650 newtons times 50 meters, which will equal 32,500 joules, or 32.5 kilojoules. This is the energy required just to lift the person. Power is measurement of the rate of which work is done or the rate of which energy is transferred. It tells us how quickly energy is delivered to a process. So power can be defined by power equals work done over time taken, or power equals energy transferred divided by time taken. Power is typically measured in watts, where 1 watt equals 1 joule per second. In construction, power might also be specified in volts for electrical supplies, for example, your single or three-phase, or horsepower, HP, for larger mechanical engines like those in excavators or some of the old pump systems. Efficiency is a crucial component in BSE. This is the ratio of useful energy output to the total energy input, usually expressed as a percentage. For an example, a photovoltaic cell might convert only around 20% of the sunlight it receives into electrical energy. The rest is lost as heat. This low efficiency means large areas of solar cells are required to generate useful amounts of electricity for a building. Similarly, a pump motor might be 80% efficient, meaning 20% of the electrical energy it consumes is wasted, primarily as heat and noise, rather than being converted into useful hydraulic power. Maximizing efficiency is a consistent goal in BSE to reduce energy consumption and operation costs. Now let's take a look at moments and equilibrium. A fundamental concept in mechanics is the theory of moments, which describes the turning effect of a force. A moment is essentially a force expressed as a bending or twisting action over a distance. So the equation could be moment of force, which would be in newtons per meters, equals force in newtons times distance. This equation explains why it's much easier to undo a tight nut with a long spanner than your fingers. The spanner increases the perpendicular distance from the pivot, so the nut, meaning you need to apply less force to create the same turning moment. Equilibrium is a state where all the forces and moments acting on the system are perfectly balanced, resulting in no net change in motion or rotation. For a system to be in rotational equilibrium, the total sum of the anticlockwise moments must be equal to the total sum of the clockwise moments. Understanding the centre of gravity is also crucial. This is the theoretical point where the entire weight of an object appears to act. For standard symmetrical shapes, it is the geonomic centre, known as an object's centre of gravity, is vital to prevent it from overturning when being lifted, moved, or installed. So, for example, a large boiler or an air and handling unit. When we look at a simple beam supporting a load, we have compression, which occurs in the top of the beam where material is being pushed together. Tension occurs at the bottom of the beam where materials is being pulled apart. And shear forces occur at the ends of the beam where the load tries to slice through the material. Engineers designing beams to withstand these internal forces, ensuring they remain in equilibrium and do not deflect excessively or even fail. So now we're going to look at simple machines and mechanical advantage. So mechanical advantage is the effectiveness of a simple machine to amplify a force. It's the ratio of the output force, the useful work done, to the input force, the effort applied. Simple machines allow us to overcome large loads with relatively little effort. So let's look at some of the common simple machines used in and around BSc. So we have levers. A lever allows an extension of force to be exerted. Think of a spade. It has a large handle, acts as a lever, allowing you to exert significant force to excavate a cable trench with less effort than digging it by hand. Even a simple crowbar used to lift a heavy object is a lever. Then we have pulleys. A pulley is a wheel and axle system used with cables to change the direction of a force or to gain mechanical advantage. Pulleys are assembled into block and tackle systems to lift heavy loads such as cranes used to hoist large HVAC units onto rooftops or within the mechanism of building lift systems. The more pulleys in a system, the greater the mechanical advantage, meaning less input force is required to lift a heavy load. Screws. A screw is essentially an inclined plane wrapped around a cylinder. A small rotational force, so torque, applied to the shaft can exert a very large axial force along the screw's length. This is why screws are so effective at holding items together, like two pieces of wood, or for precise adjustments. The pitch of the screw, so the distance between its threads, is a key. A smaller pitch means a greater mechanical advantage, requiring less effort to drive the screw in, but more turns. Then we have an Archimedean screw. This ancient invention is still relevant today. It is a twisted screw thread inside a pipe, used to lift liquids like a wastewater lifter or treatment plant, or granular materials like powders or grains in an industrial process. Interestingly, it's driven by the flow of liquid. Archimedes screws can also act as an effective turbine to generate power. Then we're going to take a look at velocity and motion. Velocity is a measure of an object's speed in a given direction. For example, a fan blade rotating at 1,000 revolutions per minute clockwise, or water moving through a pipe at 2 meters per second towards a boiler. In building services engineering, controlling velocity is critical for system performance, efficiency, and longevity. So airflows in ducts, air must move at specific velocities. If air moves too fast, it can create excessive noise, cause vibration in the ductwork, and increase energy consumption due to higher pressure drops. If it moves too slowly, it might not effectively ventilate a space or deliver heating and cooling efficiently. Water flowing pipes. Water velocity is equally important. If water flows too quickly, it can lead to corrosion, where the physical force of the water wears away the pipe material, especially at bends, and excessive noise, which we call water hammer. If it flows too slowly, sediment can build up, reducing pipe diameter and efficiency, and potentially foster bacterial growth. Pump and fan speeds. The rotational velocity of pump impellers and fan blades directly impacts the flow rate and pressure they can generate. Engineers carefully select motors and controlled systems to achieve optimal velocities for specific applications. And lift speeds. As we mentioned before, the velocity of a lift car is a key factor in a passenger's comfort and building traffic flow. Too fast and it can be uncomfortable. Too slow and it can cause delays. Velocity control's its prime example of mechanical engineering in practice, balancing various factors to achieve desired outcomes. So today we have covered the fundamental principles of mechanical science and their profound impact on the building services engineering. We started with energy, understanding its forms, kinetic and potential, and how transducers convert it. We then explored force, defining it as it push or pull, and examining the various loads and building systems must withstand. Newton's second law, F equals ma, shows us the relationship between force, mass, acceleration, crucial for sizing dynamic equipment. We distinguish between work, which is force over distance, and power, the rate of work doing work, and discuss the importance of efficiency in all building services engineering systems. We delved into moments in equilibrium, understanding turning effects, the centre of gravity, and how forces balance the structures like beams. We looked at simple machines like levers, pulleys, and screws, and how they provide mechanical advantage to amplify our efforts. And finally, we touched on velocity, highlighting its crucial role in controlling air, water flow for optimal performance and longevity. Mechanical science is the invisible framework behind every building service. Once you've started to understand these principles, you will begin to spot them everywhere. From the lift you take to class, to the hum of the ventilation system above your head, to the flow of water in your taps. They aren't just abstract theories, they are the bedrock of performing engineering. Okay, so that's it for today's episode of the Copper Connection podcast. I hope this gave you some clarity on the mechanical principle powered our industry. Next time we'll tackle another core topic in building services engineering. And remember, if you can measure it, you can manage it.
We'll be back next week. In the meantime, please subscribe and thanks for listening.